Thank you very much, the chairs. It's a great pleasure to be here talking to you in this conference. First, I would like to thank Professor Shafur Rahman for inviting me to be here talking and meeting so many bright scientists, seniors, emerging, and also some industries as well. I'm from MIT. If we talk about a specific type of oleogel, which is from waxes and biopolymer, which is ethylene cellulose. If we go and have a look at foods, many foods they contain saturated fatty acids. So those numbers there tells us that if we go and use some cheese, yes, saturated fatty acids about 65, 70, but if we go to canola oil, saturated fatty acid is very low. So how we can actually use this low saturated fatty acid composition and at the same time have the luxury of high performing solid fats in our system. Why? Because saturated fatty acids are linked with chronic diseases, that's very well known, and we are advised to cut down on our consumption of saturated fatty acid. It's not easy, and the research in this area has been going on for long. Still, papers are getting published. Why do we need oleogels? We want these products with high quality expectation of the consumers. Without oleogels and solid fat, making these products with the right organoleptic properties often is a challenge, so we need to look for replacements. Oleogels are made through different strategies. Sometimes we modify emulsions, we play with their viscosity, gels, and that's actually the right part of this slide. We structure emulsions, oil in water, water in oil, as one strategy. In many cases that generates oleogels that are often high or medium in water. So they have their own applications. If we go down here, sometimes we create porous structures and we load oil on top of that. So that's like porous starch or maybe freeze-dried systems that after freeze-drying we've got a porous structure and we can load oil on top of that and we can have oleogels. Again, they have their own position for different applications. But our work is actually focusing on direct dispersion. When we are trying to get a solid fat like lard with low moisture content, but same time good structure and also low moisture content. So we are working on this one in this presentation. This is very similar when you actually put gelatin in water. So we get water, we put gelatin in there, we heat it, we melt it, and then during gelation it creates a structure for us. But in this system, of course we can't put gelatin in oil. It's not soluble, we're looking for replacements, other gelling agents. Indeed, that's the system that we are looking for. So we want to put liquid oils inside a structure that is going to gel. And we learned it from nature. I guess we've got this system in seed oils. So nature has made this. We actually extract oil from seed oils. We destroy the structure, oil is extracted. But now we want to go back and perhaps learn from nature and see how we can make such a system. So ideal oleogels of this type are oleogels that they've got good fatty acid profiles. That's the type of the oil we use. It could be rice bran oil or canola oil or any oil that we are looking for. We are looking for physical properties similar to back fat or solid fat for specific usage and application. Of course, sensory property in terms of melting and all that is very important. And of course, processability is important. We make an oleogel and we put it through the process and it suddenly destroys, there is no use of it. And of course, cost is always very, very important for the industry if we want to upscale. If we want to replace ingredient A with B, if the price difference is more than 10%, from my point of view, often the industry would start and stop and think and whether that's going to work or not. So any cost increase more than 10%, that's a big challenge from my point of view for selling and I guess upscaling any technology in the ingredient that we're talking about. Oleogels are determined by the gelator, oil type, and the process that we actually go through to prepare them. So those are the three main parameters that are dictating the quality of oleogels of this time. The top one, I think, is perhaps about 80%. I'm just making a guess. The oil type and the process of preparation is perhaps 20, maybe up to 30%. So gelators are very important, and we'll be working and talking about the gelators. In this review paper, we reviewed some types of oleogels that we call them low molecular weights. They come in different types, of course, oleogels, small and large. And in here, this is highlighting that, yes, gelators are the main factor in this type of oleogel. Of course, we have other parameters that also they are linked with concentration, chemical composition, and the way we produce them. But those are the main parameters. Gelator, it's a single, is it a binary or tertiary gelator system, and also of course solvent phase, which that's the oil type, and also the way we process and prepare. This slide is just summarizing the two main types of oleogels that are used in this space. Some are low molecular weight oleogels. Waxes are under this. So beeswax, carnauba wax, or any type of wax are under this. Often they have a small molecular weight of up to 3,000 Dalton, but they have the property of aggregation. They come together and they make bigger structures, and then inside this bigger structure they trap oil. And to the right, we've got polymers. By polymers, some of them we work a lot with proteins and also, let's say, other polymers that are going under this. They are often hydrophilic. They don't work in this type of oleogels that we're talking about. But this research and this stuff mostly actually is focusing on gelators that we can directly put them in oil, melt them, and act as gelling agents. Example, ethyl cellulose. So from cellulose derivatives, mostly they are hydrophilic. Some of them they have many of them are hydrophilic. Some of them, like ethyl cellulose, actually they like oil. They are hydrophobic, and you can actually use them for this purpose. I'll give two examples of research in this area. One is how we can actually mix waxes to get a better property and leverage their properties in here. So this research is looking into binary wax oleogels, improving physicochemical properties and oxidation stability through substitution of carnauba wax with beeswax. Often we know beeswax, carnauba wax is another, which is emerging, is commercially available, and I think it's coming from a palm tree, which is maybe from Brazil, yes, but it's commercially available. This slide is showing just if we get some wax and put it in oil, melt it between maybe melting points of waxes are between 30 to 90, melt it, let it cool down, we get this oleogels. Looks pretty simple. So those are actually oleogels with waxes from 1% to 10%. 10% of course is very high, and there are some challenges in here when it comes to waxes. So they are very shear sensitive and also for isotropic behavior. It means if you hit them, they will lose some of their properties and quickly they change. So we want to perhaps address some of this, high concentration and also shear sensitivity and also porosity. isotropic properties. This is the research that was done. The total wax concentration was 4%, because we didn't want to go 10 or 8, because that's a lot for the industry. If they want to make oleogels, it's better to have the lowest concentration of gelatin. And what we've done is simple. So we've got 10%, 90% of each of this, and then we've moved. So we've changed that ratio. That's how it's been made, this oleogel. So we've got oil, rice bran oil in here. We've got heating stage. The oleogelator actually is mixed in here at a specific temperature. It has to be above the melting point of the oleogel. If it's beeswax, it could be low. If it's carnauba wax, it has to be higher. Mixed, again, you have to go to the temperature of the higher melting point of the gelator. And then after that, we let it cool down and we get oleogels. Pretty simple. These are some of the results of this part, which I'm sharing. So to the left, we've got 100% carnauba wax. And to the right, we've got 100% beeswax. But in between, we're changing that ratio. So that's actually 90-10, 80-20, we go to 50-50, and again, 90-10. So we can see that this carnauba wax cannot create a self-sustained oleogel. However, if we mix it with beeswax, not only its property and hardness, which is on this scale, it's been actually tested with a texturalizer, goes higher and higher, and actually it can overcome even the highest hardness of what we get from for beeswax. So we can actually play with these two and bring down the concentration that we need, at the same time increase the hardness of the system. This one, the other graph is actually oil binding capacity. Oil binding capacity is very important in oleogels because it actually binds oil. And often we're looking for something about 90%, 80%. Carnauba wax is pretty low, but if we mix, we can actually go to almost 100% on this. So that was very interesting for application, also for industry, because with this we can reduce the wax concentration needed, and also we can come up with different oleogels with different properties. The top graph in here is just oscillation rheology. It's G prime, G double prime, and it looks into the way the gel is behaving when it's subjected to oscillation. So oscillation, we can see that if we apply oscillation to oleogels, they behave differently. So this one is the critical strain, but to the right is the flow point. Again, in two different processes, we've got different shear levels, and shear stress deformation obviously is very important. So this is added to what we actually saw in the previous slide. If we have a look at the DSC data, we can see that for single wax, top and the bottom, when we get just single peaks, but when we have mixes of the two oleogelators, we get two peaks. It means that thermodynamically these two gelators don't mix. They're actually giving separate peaks to us. So we may have different melting points in here. When it's consumed, possibly depending on the concentration of each of the gelators, we may get maybe greasiness, different greasiness sort of perception in the sensory. That needs to be, of course, tested. So left is about melting and right is about crystallization. And when the concentration is 50%, again, yes, we get two peaks. That's showing that these two haven't actually mixed at the nuclear level. These are pretty simple tests, polarized light microscopy. It's showing how these gelators, two types of waxes, carnauba wax, 100% here, and 100% beeswax in here. So you can see that carnauba wax is giving us big aggregated areas, different to beeswax. But if we go to the middle, we can see that we don't have this big aggregated area, and crystallization of carnauba wax seems to be beeswax, and perhaps that's the reason we saw that big change, major change in the hardness of the system that we saw earlier on the texture analysis data. Also, our students looked into the oxidation of oleogens. As you know, oil systems oxidation is important. Since that when we move from the oil to the oleogel, this is going to change. This is actually showing the rate of the oxidation. So oxidation, when we move from single gelators to mix, it's changing. Perhaps it's just reflecting this structure. Somehow, these structures are stopping the oxidation of oleogels as we put them through days and weeks of storage. They may stop the movement of chemical compounds that are involved with oxidation, and also maybe the penetration of oxygen into the system. But we don't know exactly how that happens. But it can increase the shelf life of the oil, which sometimes is a problem for liquid oils if we have many unsaturated fatty acids. So that's the first one. Quickly I go to the second research. And in this one we looked into biopolymers. And in here is ethyl cellulose. So in the previous research we saw that yes, we can play with waxes, but there are still some problems with waxes. We thought let's see if we can address some of those problems by combining them with another biopolymer. This is large, those were small gelators. So ethyl cellulose is one of the unique cellulose derivatives that can be dissolved in oil if it has a specific degree of substitution, which is actually in here. So if we have this degree of substitution, we can actually solubilize it in oil. But there are some limitations to this. When we combine with waxes, we may address some of it. So high concentrations are required, sometimes 8 to 10%. They have high melting and glass transition temperature, so they need high temperatures to prepare, because we need to melt them. And also, plasticity is another issue with this. This is the oleogel, this one, that has been made with 8% ethyl cellulose in rice bran oil. We can make this with canola oil or any type of oil we want. These are some of the basic and preliminary tests that we did. So EC concentration, beeswax. You can see this self-sustained oleogel with different sort of colors and transparency. That's 5% EC, no beeswax, but that's again all wax, and this is in between. If we put those under light microscopy, we can see that yes, we have different crystallization level in either of those, full with wax and or mixed with ethyl cellulose and wax. So this helped us to design some experiments and get a number of samples and put them through experimentation. So we have some waxes, that some oleogels that we have got 4% EC, no wax. So the wax that we used in here is beeswax and carnauba wax mixture, because we did some work in the other first research, and we actually used the best ratio from there. So 90-10 was from there. We got that mixture and brought it into ethyl cellulose. So we wanted to leverage that capability of 90-10% of the two beeswaxes and carnauba wax. And we have a number of oleogels in here, 4% EC, 4% wax mix, and we've actually changed the concentration of each of these, but the total concentration of the oleogel is always 4%. So it's 0, 4, 3.5, 0.5, and we can go to other concentrations. Just we wanted to see how this plays out in practice. This is the way the oleogels have been prepared. So we've got oil, we heat it to a temperature above the melting point of those gelators. We drop the gelators into the system, mix, let it to melt, and then after that we let it to cool down, and we have now, let's say, oleogels to be tested. These are pictures of the oleogels with different ratio concentrations of ethyl cellulose and wax. So this is 100% wax, mixture of beeswax and carnauba wax, 10-19. That's the structure. And this is 100% EC, ethyl cellulose, and these are in between. You can see some differences in terms of visual appearance of the oleogels. This one is a bit softer, this is a bit grainier, but in between we can play with that softness and coarseness of the texture, and of course with the hardness of the oleogels too. These are some pictures made with atomic force microscopy. We get oleogels, we put it under atomic force microscopy, and gives us some insights about the coarseness and also structure of the oleogels. And we can see if we have, let's say, wax crystals or they have been suppressed in terms of crystallization. But this one is 100% wax, and this one is 100% EC. You can see that the structure is different. So you can see crystals in here, but as we move and we increase EC, the texture changes. So that texture, that crystallized texture, we can't see as we move towards EC. So EC is helping to control crystallization. Also, in terms of the roughness, these waxes these oleogels are different when we actually play with different concentrations. If we go and have a look at other properties, this is produced from a texture analyzer. So you get oleogel, you put it under a probe and just compress it and look into the force. So these oleogels, these ones are, the red one is when you have only wax. It's unpredictable, it breaks. It's hard at the same time. But when it goes to perhaps processability, this is unpredictable. However, if we go and mix wax with ethyl cellulose, we can come up with oleogels that are more predictable, and this brittle structure is gradually controlled. But the hardness is decreasing. So we need to find a balance, which one we want in practice. So that is telling us that if we mix waxes and ethyl cellulose and get pressure, we come up with different textures. And for example, this one, to the right, cohesiveness. This is telling us if we put these oleogels through processing, how stable they are. Cohesiveness is tested when you actually put double stress on the oleogel. It's telling us that if you actually work with only wax, cohesiveness is low, but if we mix wax with ethyl cellulose, we can increase cohesiveness. So if we work with the oleogel in the process, this will be more stable if we use the mixture. Of course, hardness is compromised, as you can see from this slide and these values in here. And oil binding capacity again differs. So when we go to wax, we have the highest oil binding capacity, but with ethyl cellulose, we get that compromised. With that, I'm going to my last slide before I'm told by the chair to stop. So this is my last slide that I would like to just perhaps talk about the model that is perhaps telling us what's going inside those data that we discussed. So to the left, this is actually a system that perhaps is showing what's happening in the binary wax. So we had two waxes. One was beeswax, another one was carnauba wax. Beeswax has got a low melting temperature, and carnauba wax has high melting temperature. Carnauba wax has big crystals, beeswax has small crystals, and perhaps that's telling us what's happening in this space. So we have a mixture of large, small crystals, but when we mix them, beeswax is able to control the crystallization of carnauba wax. Then, instead of having carnauba wax to be disturbing, to be destroying the structure, beeswax, if it's mixed at the right concentration with carnauba wax, they will have synergistic effects. So they can increase the texture properly. If we go to others, for example, this is ethyl cellulose. Ethyl cellulose is like when you put gelatin in water, it dissolves completely. If we heat it to the right temperature, let's say 115 degrees C, and when it cools down, it creates random structures, three-dimensional network, and then it entraps oil, and we get this oleogel in here. This is the model that actually is for the second part of my talk that we just finished, when we have binary waxes and ethyl cellulose. Based on what we saw, this binary system is the best. We use the capacity of ethyl cellulose and waxes and come up with a system that is going to benefit from the mixture of waxes and also ethyl cellulose at the same time. So we can use these three types of chelators in combination so that we go to the right type of oleogels that we want. With that, I'm going to stop here. This is our research team and colleagues, and also that's the name of my PhD student who did a lot of work in this space, and also I learned from her as well when she was doing a PhD. And with that, I'd like to stop, and thank you for your listening.